Hey everyone, welcome back to my channel. Today we're diving into one of the essential concepts in programming, user-defined functions. User-defined functions in programming help keep code clean, organized, and manageable by grouping related statements together. This avoids code repetition, reducing errors, and simplifying the main program. Let's take a closer look at the given example. The program initially converts Fahrenheit to Celsius in three separate places by repeating the formula for each temperature value. This repetition makes the code longer and introduces the risk of errors, as seen in the incorrect calculation for F3 in the example. Such redundancy not only clutters the main program, but also makes it more challenging to maintain or debug, as a mistake in one place can go unnoticed. Defining a function like F2C for Fahrenheit to Celsius conversion simplifies the program by centralizing the calculation, allowing us to call F2C of F1, F2C of F2, and F2C of F3 without rewriting the formula. This reduces redundancy, minimizes errors, and keeps the main program cleaner and more readable. Functions are especially effective for complex or repetitive tasks, but are equally valuable for organizing operations into structured, intuitive blocks, making the code easier to maintain and promoting efficient programming practices. Functions are essential for organizing and reusing code by grouping statements into named units. A function has two main parts: the definition, which specifies its name and contains the block of statements to execute. The animation demonstrates how the calc pizza area function calculates the area of a pizza using the formula for the area of a circle, PR2. Inside the function, the value of p is stored in pi_val. The pizza diameter is set to 12 inches, and the radius is calculated by halving the diameter. The area is then computed using the radius and pin_pip and returned by the function. When the function is called, execution jumps to its statements, performs the calculations, and returns the result. Control then returns to the original call location, where the pizza area is displayed in a formatted message. This example highlights how functions break down complex tasks into reusable, organized components, improving code readability and maintainability. Alright, now it's your turn to put this concept into action. Let's see how well you've grasped the basics of functions. I've got a few fun practice questions for you to tackle. Take a moment to think about them carefully and share your answers in the comments section below. Here are some intriguing questions about the program and the calc pizza area function we discussed earlier. Take a closer look at the code and think critically. Can you figure out how many times the function calc pizza area is called? How many times is calc pizza area actually defined in the program? How many output statements will be executed overall? And finally, can you spot how many print statements exist within the calc pizza area function itself? Put on your thinking cap, analyze the program carefully, and share your answers in the comments. I can't wait to see how many of you nail this one. When a program starts executing, it begins from the main function or the entry point of the code. At a certain point, a function call is encountered, which transfers control from the main program to the called function. This transition is depicted by an arrow leading to the function definition, where any provided arguments are passed as parameters. The function then executes its statements sequentially, performing its designated task. Once the function completes its execution or encounters a return statement, control is transferred back to the main program, specifically to the line immediately following the function call. The function's output, if any, is also returned at this point. Finally, the program resumes execution and displays the result. A return statement in Python allows a function to send a result back to where it was called, enabling further computations. This makes functions not only reusable, but also efficient tools for producing results that integrate seamlessly into larger programs. The program provided offers a clear demonstration of this concept. The function compute_square is designed to calculate the square of a given number. When the function is called with the value 7, this value is passed as an argument to the parameter num_square. Inside the function, the square of the number is computed using the formula 2c, and the result is returned to the calling code using the return statement. The returned value is then assigned to the variable num squared, which is used to display the message 7 squared is 49. This example shows how return statements make functions versatile by producing results that simplify code structure and enhance readability. Alright, after discussing the concept of return statement, let's put your understanding to the test with some practice questions. Here's the first question. How would you complete this function to return the sum of num1 and num2? Put your thinking caps on and share your answers in the comments. Let's see who can get it right. Here's the second question. Can you add a return statement to compute the cube of a number? Think about the formula and let's see your solutions in the comments. In programming, parameters allow functions to accept input, enabling them to perform different tasks based on the provided values. A parameter is a named input defined in the function which influences its behavior. For example, a function to calculate the area of a pizza might have a parameter for the pizza's diameter. When calling the function, the argument is the value passed to the parameter, such as calc pizza area 12.0 or calc pizza area 16.0, where 12.0 and 16.0 are arguments. A parameter works similarly to a variable. Taking the value of the argument when the function is called, it forms a shared reference to the argument within the function, but once the function exits, the parameter no longer holds that value. Arguments can also be expressions, such as x times 1.5, which allows for dynamic calculations during the function call. Now it's time to test your knowledge. Let's see how well you grasp the concepts of parameters we've covered. I'll present some practice questions in front of you. Here comes the first question. Can you complete the function to accept a parameter named numGrade? What's the missing piece in this definition? Take a guess and let's see who gets it right. Here comes the second question. Can you call a function named calc_calories and pass the value 21 as an argument? Let's see how you approach this one. Type your answer in the comments. Now, let's dive into multiple or no parameters. When defining a function with multiple parameters, each one is matched with an argument in the call. First parameter to the first argument, second to the second, and so on. This program defines the calc pizza volume function, which calculates the volume of a pizza using its diameter and height. It computes the radius, calculates the area with pi r squared, and then multiplies the area by the height to find the volume. The program prints the volume of pizzas with different dimensions, formatting the results to 3 decimal places. For example, a 12.0 by 0.3 inch pizza has a volume of 33.929 cubic inches. A 12.0 by 0.8 inch pizza has 90.478 cubic inches, and a 16.0 by 0.8 inch pizza has 160.850 cubic inches. The program demonstrates the use of functions with multiple parameters and formatting in Python. Now, let's put your skills to the test. Let's see how well you can apply what you've learned about multiple or no parameters. I'll ask a few questions, so take a moment to think carefully before you answer and type your answer in the comments. Ready? Here's the first question. When calling a function, how do you pass 2 integer arguments to it? Time for second question. Given the function definition, what value does b receive during the function call? Think about how function calls work and decide which option makes the most sense. Let's see who can figure this out. Hierarchical function calls or nested function calls occur when one function is invoked within another, enabling modular and efficient code reuse. In the provided program, the calc pizza calories function calculates the total calories of a pizza by invoking the calc circle area function to determine the pizza's area. First, calc circle area computes the area of the pizza using the formula area equals p times radius squared, where the radius is derived from the pizza diameter. This area is returned to calc pizza calories, which multiplies it by the calorie density constant, 16.7 calories per square inch, to calculate the total calorie content. The result is then formatted and displayed using the print function. For a 12-inch pizza, the program calculates 1,888.73 calories, and for a 14-inch pizza, It calculates 2570.77 calories, showcasing how hierarchical function calls streamline complex operations by breaking them into smaller, reusable components. Now that you understand the concept, let's put your knowledge of hierarchical function calls into practice. Let's dig into some pizza math. Your task is to complete the function calc pizza chad calories per chad slice. First, focus on the total calories for the whole pizza. What should you type for placeholder A to calculate this? Remember, the function calc pizza calories is your key to figuring this out. Ready to tackle this challenge? Now we discuss another topic, printing text. Printing text is a common task for functions in Python. However, adding multiple print statements directly in the main program can quickly make your code messy, especially if the same text needs to be printed repeatedly. When writing a program, including print instructions in the main code can clutter and complicate readability, especially with repetitive outputs. A dedicated print function streamlines text output, keeping the main program clean and organized. For example, you can define a function like print summary to format and print specific information. The main program simply calls this function whenever needed, passing the required parameters. The function then executes, prints the formatted output, and completes its task by returning control back to the main program. This approach not only simplifies the structure of your code, but also makes it more modular and easier to maintain. Now, let's put your skills to the test. Let's see how well you can apply what you've learned about printing from a void function. I'll ask a few questions, so take a moment to think carefully before you answer and type your answer in the comments. Ready? Here's a question for you. Do all print operations have to be performed directly in the main program? Think carefully. Your answer might surprise you. Here's another one for you. Can a void function have any number of parameters? Here's the last one for you. Are print operations required to be done only in the main program? What's your answer? Match your answer with correct one and share your thoughts in the comments. Let's talk about one of the biggest advantages of using print functions in your code, reusability. A key advantage of using a print function is the ability to write complex output statements just once in your code. Using a print function greatly enhances the organization and efficiency of a program. For instance, a print function allows you to centralize complex output statements, reducing redundancy and clutter in the main program. This becomes especially useful when outputs are repeated. In one example, program A writes the same formatted output twice directly in the main program, while program B uses a single function, print greatest, and simply calls it twice. This eliminates the need to duplicate the output code. Furthermore, if changes to the output are needed, such as adding an exclamation mark, program B requires the change to be made only once in the function, which automatically updates every instance where the function is called. In contrast, program A requires changes to be manually made in every occurrence of the print statement, which is time-consuming and prone to errors. This highlights how a print function keeps code cleaner and more maintainable. Now that we've covered the concept of calling a print function multiple times with example, it's time to put your knowledge to the test. Are you ready to see how well you've grasped these concepts? Let's dive into some quick questions to check your understanding. Think carefully and type your answers in the comments for me to review. Here comes the first question. To print the greatest word on earth with 10 different words in program B, how many times do you think the main program needs to call print greatest? Here comes the second question. If you want to change the phrase from on earth to in the galaxy, how many statements would need updating in program A and program B? Think it through and drop your answer below. This example demonstrates a simple Python menu system that uses a function and a loop to provide an interactive experience. The print menu function displays a menu with three options: Gumbo, Jambalaya, and Quit. A while loop ensures the menu repeatedly appears until the user selects option 3 to quit. Inside the loop, the user's choice is captured using input. If the choice is 3, the program prints goodbye and exits the loop by setting quit program to true. For other choices, the program displays the corresponding order. This example highlights how functions and loops simplify code organization and enable reusability while providing a seamless user experience. Alright, after discussing the concept of menu system with the help of example, let's put your understanding to the test. Here's the question 1. In the menu system example we just discussed, how many times is the print menu function called during the program's execution? Here's the last question. In the menu system example, which of these statements, if added to the print menu function, would make it no longer a void function? Think it through and let us know your answer below. Now it's time to discuss about dynamic and static typing. Dynamic typing allows the type of a variable to be determined at runtime, meaning you can assign a value. In contrast, static typing requires you to declare the variable's type at compile time and it cannot change. The function's behavior of adding together different types is polymorphism. Polymorphism is an inherent part of the Python language. In this example, we're working with a polymorphic function called addXY, which can accept different types of arguments and behave accordingly based on the input. Polymorphism allows us to write a single function that can handle various data types, providing flexibility to the programmer. When the function is called with two integers, such as add57, it performs an addition operation. The add function recognizes that both x and y are integers and returns the sum, which in this case is 12. The function behaves as expected by performing simple arithmetic with numeric data. On the other hand, if the function is called with two strings, like add Torah, Bora, the behavior changes. Instead of performing addition, the function recognizes that the arguments are strings and concatenates them. The result is the combined string Torah Bora. This ability to handle different data types with the same function is an example of polymorphism in action. Now that we've covered the basics of static and dynamic typing, let's see how well you've grasped the concept. I've got some quick questions for you to try out. Take a moment to think about your answers and drop them in the comments. Here's the question 1. Does polymorphism refer to how an operation behaves based on the types of objects involved? Think carefully and let me know your answer in the comments. Here comes the next question. Can a programmer pass only string arguments to a user-defined function, or is there more flexibility in the types of arguments? What do you think? Let's move on to question 3. In static typed languages, do you think every variable's type must be explicitly defined in the source code? Is this statement true or false? Match your answer with correct one and share your thoughts in the comments. Functions in programming help organize code, improve readability, and make maintenance easier. As programs grow, they can become hard to manage without a well-structured approach. Functions break the code into smaller, manageable tasks, improving clarity and simplifying debugging. The program example demonstrates the practical use of functions to simplify calculations and improve code organization. It defines two functions, steps to feet, which calculates the total distance walked by multiplying the number of steps by 3 feet, and steps to calories, which calculates the calories burned by first determining the time spent walking and then multiplying by a calorie burn rate of 3.5 per minute. In the main program, the user inputs the number of steps walked, and the values are passed to both functions for calculation. The program then outputs the distance in feet and the calories burned in a clear format. This approach illustrates how using functions can enhance readability, modularity, and maintainability in programming. Next, this example program demonstrates a program that calculates the distance walked and calories burned directly within the main program without using user-defined functions. The user inputs the number of steps walked, and the program calculates the total distance in feet by multiplying the number of steps by 3. It then calculates the calories burned by first determining the time spent walking and multiplying it by the calorie burn rate of 3.5 per minute. The results are displayed in a simple format showing both the distance in feet and the calories burned. Alright, it's time to test your knowledge. Take a moment to think through each question and share your answers in the comment section for me to review. Here's the first question. In the example without functions, how many statements do you think are written in the main program? Take a closer look and let us know your guess in the comments below. Here's the second question. In the example with functions, how many statements are there in the main program? Think carefully, match your answer, and share your answer in the comments. Now we discuss another topic, mathematical function. Mathematical functions in Python are pre-built tools that make handling numbers incredibly efficient. Instead of manually writing algorithms for every calculation, Python provides us with a wide range of functions for tasks like finding square roots, calculating exponents, generating random numbers, or even working with trigonometry. The program demonstrates the use of a function to convert a person's height, given in feet and inches, into centimeters. First, it defines two constants, cm per inch and inches per foot. These constants represent the number of centimeters in 1 inch, 2.54, and the number of inches in 1 foot, 12, respectively, and are stored in the global frame. Next, a function named height US to km, feet, inches, is defined. This function takes two numerical parameters, feet, the height in feet, and inches, the additional height in inches. Inside the function, the total height in inches is calculated by multiplying the feet by inches per foot and then adding the inches. The total height in inches is then converted into centimeters by multiplying it by cm per inch. Finally, the result in centimeters is returned. When the function height US to cm64 is called with the arguments 6 for feet and 4 for inches, the function performs the calculations in its local frame. The total height in inches is determined as 612, par 4 76 inches. This is then converted into centimeters. The function returns the value 193.04, which is displayed as the output. Functions can be powerful tools when used within expressions. When a function is called within an expression, it evaluates to the value returned by the function. When calling functions within expressions, the function evaluates to the value it returns, making it possible to integrate functions directly into mathematical operations. For instance, in the program example, the function compute square is called twice within an expression. In the first step, compute to square 7 is executed, where the value 7 is passed to the function. The function calculates 7 times 7 equals 49 and returns 49, which becomes part of the expression. Next, in the second step, compute square 9 is executed. Here, 9 is passed as the argument. The function calculates 9 times 9 equals 81 and returns 81, which is also added to the expression. Finally, the expression evaluates to 49 plus 81 equals 130, and this result is assigned to the variable C2. In the last step, the print statement executes, outputting 7 squared plus 9 squared is 130. This program demonstrates how functions can streamline calculations by directly embedding their calls into expressions, producing clean and efficient code. After discussing the concept of calling functions in expressions with the example, let's test your understanding with some practice questions. Think carefully about the questions and share your thoughts in the comment section below. Here comes question 1. Take a look at this line of code. Do you think it's valid or invalid? Think carefully about the function definition and drop your answer in the comments, and let's see if you're on point. Here comes question 2. Check out this line. Is this valid or invalid? Think about how assignments work in Python. Does this line make sense? Drop your answer in the comments and let's see who gets it right. Now, move to another topic, function stubs. In software development, incremental development is a strategy where programmers write and test small pieces of code at a time, ensuring each part works before moving on. A key tool in this process is the use of function stubs, placeholders for functions that are defined but not yet implemented. Function stubs allow developers to focus on the high-level behavior of the program while deferring implementation details. The pass keyword is commonly used to create a function stub, allowing it to exist without performing any operations. The example program demonstrates the concept of function stubs in action. The program is designed to calculate the distance in feet and the calories burned based on the number of steps walked. The program starts with two functions, steps to feet and steps to calories. The steps to feet function is implemented and takes the number of steps as an argument, multiplying it by 3, the assumed number of feet per step, to return the total distance in feet. However, the steps to calories function is a function stub, is defined but not yet implemented. In the early stages of development, this stub allows the program to continue functioning without errors, while the developer can focus on the high-level logic of how the program should work. The user is prompted to input the number of steps walked, and the program calculates the corresponding distance in feet. The placeholder function for calories, which doesn't yet do anything, still gets called to maintain the structure of the program. This demonstrates how function stubs allow for early testing of other parts of the program while leaving room for future development. The updated steps to calories function in the example demonstrates another useful approach when using function stubs, printing a message to alert the user that the function is incomplete. In this case, the stub includes a print statement displaying "fix me, finish steps to calories." This acts as a reminder or warning for the developer or tester that the function still needs to be implemented. Additionally, the stub returns -1, which is a common practice for functions expected to return a value but are not yet fully implemented. Returning -1 serves as a placeholder to indicate an invalid or temporary result, ensuring the program does not break during testing. This approach preserves the program's structure and functionality while highlighting unfinished areas, simplifying debugging and incremental testing. The provided program example demonstrates the use of a NotImplementedError to signal an unfinished function, stopping the program's execution when the getPoints function is called. The getPoints function is intended to collect user input and return a list of XY coordinate tuples. However, this function is currently a stub, as indicated by the raised NotImplementedError statement. This placeholder prevents the program from running further without completing this essential functionality. The side length function calculates the distance between 2 points using the distance formula involving math.sqrt. The getPerimeterLength function takes a list of 3 points, calculates the lengths of the 3 triangle sides using side length, and sums them to return the perimeter. The program aims to calculate the perimeter of a triangle using 3 points provided by the user. When executed, the program attempts to call getPoints3, but since this function raises a NotImplementedError, the program stops execution and displays a traceback error, ensuring that missing implementations are addressed before further execution or testing. Now that you have learned about incremental development and function stubs, let's put that knowledge into action with a few practice questions. Take your time to work through each one, and don't forget to share your answers in the comments below. Here comes the first question. Incremental development involves writing and testing code in small steps, but does this approach ultimately speed up the development process? Think carefully about this question and share your answers in the comment section. Here comes the second question. Function stubs are great for organizing and planning your code, but do they have an impact on how fast your program runs? Think it through and drop your answer below. True or false? Let's see who gets it right. A common error many programmers face arises from copying and pasting code between functions without completing all necessary modifications. While copying and pasting can be an effective way to save time and reduce effort, it's essential to ensure every part of the code is adjusted to fit its new context. The example program contains 2 functions, one that converts Celsius to Fahrenheit, and another that attempts to convert Fahrenheit to Celsius. While the first function, Celsius to Fahrenheit, works correctly by applying the appropriate conversion formula and returning the Fahrenheit value, the second function, Fahrenheit to Celsius, contains an error. The logic for converting Fahrenheit to Celsius is correct, but the function mistakenly returns the Fahrenheit value instead of Celsius. This error occurs because the code was copied from the first function without fully modifying it for the second function's purpose. This highlights the importance of carefully adjusting copied code to ensure it works properly in its new context. The return statement in Fahrenheit to Celsius should be corrected to return the Celsius value for accurate results. Return errors in Python can cause unexpected behavior. A common mistake is returning the wrong variable, such as using return temperature instead of the correct one, which might work occasionally but leads to inconsistencies. The provided program illustrates the issue of a missing return statement. The function steps to feet is designed to calculate the distance in feet based on the number of steps. It defines the conversion factor as 3 feet per step and calculates the total feet by multiplying the number of steps by this factor. However, the function does not include a return statement to send the calculated value back to the caller. In the program, additional variables are initialized, such as steps, which is set to 1000, and the function is called with steps as the argument. Since there is no return statement in steps to feet, the function returns none, which is then assigned to the variable feet. When the program attempts to print the distance walked using this variable, the output is distance walked in feet. This example highlights the importance of always including a return statement in functions that are expected to return a value. Without it, the function will return none by default, leading to incorrect or confusing program behavior. Now, let's test your understanding. Let's see how well you can apply what you've learned about the common function errors. I'll ask you a few questions, so think carefully before you answer. Here's your first question. Returning the wrong variable from a function. Do you think this is a common mistake? Is it true or false? Think it through and share your answer in the comments. Here's your second question. Take a look at this function that's supposed to return the square of an integer. Is it correct as written, true or false? Think carefully and lock in your answer. In conclusion, mastering user-defined functions is a game changer for writing clean, efficient, and maintainable code. By organizing programs into smaller, reusable modules, functions reduce redundancy, minimize errors, and enhance readability. Whether you are managing parameters, building interactive menu systems, or calling functions within expressions, they streamline complex tasks and improve overall efficiency. We've explored practical examples, tackled common errors, and highlighted the power of incremental development with function stubs. Remember, understanding and applying these concepts is not just about solving problems. It's about building smarter, more flexible, and scalable programs. If you enjoyed this tutorial, please like, comment, and subscribe to our channel. See you in the next video.